TESS will fly in a special highly elliptical orbit that maximizes the amount of sky the spacecraft can image. Once TESS is launched, it will expand its orbit until it can get a gravitational assist from the moon. This slingshot will move it into a stable orbit that is tipped at about 40 degrees from the moon's orbital plane. TESS orbits Earth in exactly half the time it takes the moon to orbit once. This feature helps stabilize the spacecraft's orbit against tugs from the moon's gravity. TESS will spend most of its 13.7-day orbit observing the sky. As it approaches Earth, TESS will rotate and transmit all its accumulated data to scientists on the ground. Over 2 years, this will allow TESS to study nearly the entire sky and potentially find thousands of new exoplanets.
Okay, hopefully you could get the gist of what was going on there. So basically now TESS is in this very elliptical orbit, going out to the distance of the moon's orbit and back to Earth every 2 weeks. So we get a dump of data every 2 weeks from TESS. And when the comment about downloading data for scientists on Earth, that's me and that's you, because you're going to hear this theme the entire time. As these data are public, they become public about a month, just as soon as the data are processed. This is TESS before launch, and you can see it's a relatively simple satellite conceptually. You've got the 4 cameras, and we'll show you how those are oriented. The solar cells, and then the download dish on the front there, and then of course the electronics to run everything inside. This shows how the cameras are aligned, and you'll notice that they're stacked, the fields of view are stacked on top of each other. So, let me get it caught up here. So you get this 24 by 24 degree field of view, which is a huge field of view on the sky to start with, and then you stack 4 of those, and you get an entire quarter slice of the sky. It's 96 degrees actually, for each observation. And then each of the 4 cameras has 4 CCDs itself, so you get a total of 16 images for one TESS field. And we'll talk about how those, the time series part of those later. TESS advances every 27 days to a new field. This has finished surveying in the southern ecliptic hemisphere. It's now surveying the northern hemisphere. We have the first 3 sectors of data on the ground doing follow-up already, and the 4th sector, which is sector 17, is in analysis right now. Will be released soon. A key thing to note is the orange regions at the ecliptic poles get observed for the full year with the overlap of the sectors. So we get an entire year of data there. We can dig deeper down in planet sizes, and we can dig deeper for longer transits, longer orbital period planets in that region. Okay, so where are we now? This is almost a full montage of the southern hemisphere, and then in this image the 13th sector was added. So as I've said, the southern hemisphere is now complete. We have moved to the north. There was a little bit of a snag in the north where the old moon and Earth are causing problems. There's scattered light off of both, and this would make it impossible for the camera that would normally be in this region of space would not be useful for transit detections. So it was decided to push all 4 fields further away from the ecliptic plane. So we get this overlap region. at the ecliptic pole, which will let us search for longer period planets in that region. The downside is we get this gap in the sky that we will not have coverage on in the prime mission. So this entire sequence takes 2 years, and that's the length of the primary TESS mission, which will end next July. So what do we actually get from the spacecraft? Well, it's a time series of images, and they come in 2 formats. The first, look at the bottom part, so a little bit easier to follow, is the 30 minutes cadence, what's called full frame images. We get a snapshot of the sky for this entire region every 30 minutes. That's not one snapshot every 30 minutes. The light is integrated for that entire time. Those are stored on the spacecraft and compressed, and they're downlinked on every orbit as the satellite comes back close to Earth. The second data product is what's called the postage stamps. The postage, there are 15,000 pre-selected stars that get these postage stamps, and the TESS input catalog team went through and searched all stars before launch to decide which ones would be the best ones to search planets around. So those got assigned their own little block of memory on the spacecraft, and we store those images every 2 minutes, so we have better time resolution for those stars. There's generally 10 by 10 pixels, and that brings up another point. The pixels for TESS are 21 arc seconds, and I don't know if you've done observing before. 21 arc seconds is huge for a telescope pixel. Like the half-meter telescopes we have at Moore Observatory are about a half of an arc second per pixel. So there's a factor of about 40 or 50 difference in the spatial resolution that we can get even with our modest telescopes here at University of Louisville compared to this. The key thing for TESS though is photometric precision, and we get exquisite photometric precision with TESS. And the point is we have a huge ground-based team to do the spatial precision. These data are processed by what's called NASA's SPOC pipeline that's ran out of NASA Ames. It's the same pipeline that was used for the Kepler mission. And these people know what they're doing. The data that come out are pristine. So we're very lucky to have them join the TESS team to do this work. There's also a second, I should say that they process only these postage stamps. They do not process the full field images. MIT has a separate pipeline called Quick Look Pipeline. It's not really a Quick Look pipeline anymore. It is the pipeline for the full frame images. And you'll probably hear me refer to that as QLP, for Quick Look Pipeline. Okay, so we get these images. How do we find a planet now that we've got bazillion stars in all these images? Well, the pipelines run and they spit out reports. Every time they see a threshold crossing, as it's called, a dip in the brightness of a star, they will create a threshold report. Those threshold reports come to us at the CFA and MIT, and we review them and we decide which ones look to our eye to be good planet candidates. They're still, we can't say from photometry alone that they're planets, but we can say they're good planet candidates. We've started using some machine vetting up front to do that, but we still get together as a group and review every single one before it's published on what we call the TOI catalog. And this is a list of all the places and times to look on the sky to see if you can confirm that there's actually a transiting planet there. This is an example of one of the data sheets that we review to decide what might be a planet and what's not. The top row is the entire 27 days of data from TESS for one star. And so if you can see from back there, every other one, the dip is shallower than the other. That indicates that it's more than likely an eclipsing binary system, and the secondary star being smaller than the primary, so they create different depths in brightness. And then we phase fold those. You can see the different depths when you phase fold them there too. The bottom line is this one is expired as an eclipsing binary, and we do not publish it as a planet candidate. This is another example. This is what we do want to see. You can see the two blue arrows at the bottom here pointing at the detections of these dips in the light curve. If you phase fold those together in time and lay them on top of each other, the two dips, then you get this light curve, which shows the full orbital period. And what we're looking for there is another dip that might be a secondary. And we don't see one in this light curve, so we're still looking good as a planet candidate. The third light curve down here is just to zoom in around this region here, so we can see the shape of the light curve and assess the quality of the candidate there. And then we look again